We know when two permanent magnets of the same polarity are brought together, the magnetic fields repel each other, with the magnetic forces causing the magnets to be pushed away from each other. When two permanent magnets of opposite polarity are brought together, the magnetic fields attract each other, with the magnetic force causing the magnets to be pulled towards each other. We have therefore used magnetic energy to produce mechanical energy, or movement. This is basically how an electric motor works. But rather than have two magnets face each other to create backwards or forwards movement, we typically arrange a bunch of magnets into a circle and then place another magnet at the center of the circle. By bringing the magnets that make up the circle in and out, we can make the magnet at the center of the circle rotate. We have therefore created rotation, which can be used to drive things such as fans, pumps, pulleys, or even the wheels of a car. Now we are getting very close to how an electric motor actually works. If we replace the permanent magnets with electromagnets, which remember are just copper wires wound into coils, the strength of the electromagnetic fields, and thus the electromagnetic forces, which cause the central magnet to rotate, can be controlled by controlling the magnitude of electric current, or voltage, where current is the flow rate of electrons inside the coils, and voltage is the force pushing those electrons. This allows us to control the speed of rotation. Notice how we are using electrical energy to produce electromagnetic energy and in turn mechanical energy in the form of rotation. This is pretty much how an electric motor, specifically a direct current DC motor, works. Notice how the electrons in the coils are flowing in just one direction as per direct current. If we return to our permanent magnets for a moment, rather than bring the magnets that make up the circle in and out, we can also make the magnet at the center of the circle rotate by switching the polarities of those magnets making up the circle. But again, if we replace the permanent magnets with electromagnets, which carry an alternating current, the strength of the electromagnetic fields, and thus the electromagnetic forces, which cause the central magnet to rotate, can be controlled by controlling the magnitude of electric current, voltage, or frequency, where frequency is how often the alternating current alternates its direction. This allows us to control the speed of rotation. Again, notice how we are using electrical energy to produce electromagnetic energy and in turn mechanical energy in the form of rotation. This is pretty much how an alternating current AC motor works. An electric motor is a device that converts electrical energy into electromagnetic energy and then into mechanical energy. Although there are several different types of electric motor, including direct current DC motors and alternating current AC motors, and then several different types of motor within those two broad categories, all electric motors use these fundamental principles of electromagnetism, and they all have two key components. Number one, magnets or electromagnets, which are stationary, which we call the stator, and number two, magnets or electromagnets which rotate, which we call the rotor. The differences between the various different types of electric motor then come down to how they go about arranging the stator and the rotor, the electromagnetic fields, and the electromagnetic forces. One of the most common types of AC motor, particularly found in electric vehicles, is the permanent magnet motor. Here we can see the copper coils or electromagnets which make up the stator, and the permanent magnets which make up the rotor, after which the permanent magnet motor is named. Although there are many other types of AC motor, we will use this one, the permanent magnet motor, as an example to learn how the AC motor works, since the construction of the permanent magnet motor is pretty straightforward. For now, let's forget about the rotor and just focus on the stator. The main body of the stator, known as the stator core, has a number of teeth. In this design we have 6 teeth. A copper wire is then wound around each tooth of the stator core to form coils or windings. In this design we have 6 teeth and therefore 6 copper windings. In practice, especially for electric vehicles, there will be many more teeth and windings than this, typically at least 24, but we will limit ourselves to just 6 in order to make things easier to visualize. The number of teeth and therefore windings is almost always a multiple of 3. That's because the windings are grouped into 3 sets, or phases, as shown here in red, yellow and blue. Almost all AC motors use 3 phases like this. Since we have 3 phases, and in our design we have 6 windings, we have 2 windings belonging to each phase, and they are arranged symmetrically so to be opposite each other. No matter how many windings we have in total, they will always be arranged symmetrically like this. Here is a more realistic example with 24 windings. Let's return to our simplified example with just 6 windings, so we don't get too confused. Each set of windings is connected. Let's remove the stator core and the rest of the motor and spread the winding sets out so we can see them more clearly. For now, we will look at just the red winding set. As electric current flows through the winding set, each side of each winding generates an electromagnetic field perpendicular to itself. Since current is flowing on each side of each winding in a different direction, as the current loops around the winding, the polarity of the electromagnetic field on each side of each winding is opposite. We therefore have 2 electromagnetic fields per winding, which combine to create a complete electromagnetic field, with the familiar field lines looping around and running from north to south in much the same way as with a bar magnet. The electromagnetic fields from both windings in the set then combine, since they are directly opposite each other and with opposite polarities. If we apply an alternating current, with the direction of current alternating backwards and forwards, then the polarity of the electromagnetic field also alternates, and moreover, its intensity increases and decreases in synchronization with the current. If we do this for all 3 winding sets, we end up with 3 alternating electromagnetic fields. If current flows through each winding set out of synchronization with the other winding sets, as per 3-phase alternating current, and we bring our 3 windings back together, then we have created a rotating electromagnetic field, also known as an RMF. This is the job of the stator. The rate at which the electromagnetic field rotates is equal to the frequency of the AC supply. A 50 Hz AC supply means the AC current in any given winding is changing direction 50 times every second, and this also means the rotating electromagnetic field completes 50 rotations around the stator every second. So we understand the job of the stator. Now let's bring the rotor back in, which remember is made up of permanent magnets, in this case 6 permanent magnets. Each of the 6 permanent magnets produces a magnetic field. Notice how the poles of the permanent magnets are arranged alternately. To make things easier to visualize, we can simplify the 6 magnetic fields into one combined field. We will call this the rotor field. Now let's bring the rotating stator field back in. Again, to make things easier to visualize, let's simplify the rotating stator field by ignoring the pulsating intensity of each phase and just focus on the nature in which the poles effectively rotate around the stator. We will colour these stator poles orange so not to confuse them with the rotor field shown in white. While we are at it, we'll also get rid of the rotor field lines so to leave us with just the poles. So stator poles are shown in orange, rotor poles are shown in white. Now let's place the rotor inside the stator and let's rotate the stator field by 30 degrees, which we can do in practice simply by changing the starting sequence of the 3-phase stator field. The attractive and repulsive forces between the rotor field and stator field are shown by the green arrows. These forces are what generate torques, shown by the yellow arrows, around the rotor. Notice how all the torques are produced in the same direction, and since the attractive and repulsive forces are almost tangential to the rotor, they have the longest lever arms possible, which we can visualize by the length of the green arrows. Since torque is the product of force and lever arm length, this gives us the largest torque values possible. The rotor will maintain this position since it will be locked together with the stator field and thereby spin at the same speed, in perfect synchronization with the rotating stator field. Along with the permanent magnet motor, 2 other common types of AC motor are the induction motor and the internal permanent magnet reluctance motor. Each of these motors has a slightly different rotor construction, with different pros and cons, but they all have exactly the same stator construction and they all work in fundamentally the same way, with electromagnetic forces between the stator and rotor causing the rotor to rotate, and with the speed of rotation controlled by the frequency of the AC supply.